we are going to talk about the physics of wimps. That's not me, I'm not the wimp. So I'm Emily, I'm a physicist, or at least I will be if I ever submit my PhD. I've wanted to be a physicist since I was 4 years old. It means I've always known the answer to the question, what do you want to be when you grow up? My parents, very proud of me, thank you for asking. Other people, slightly concerned. But I wear my nerd badge with pride. And it also means that I can safely say I've never been boring at a party because I've never been to one. So, physics. The study of everything around us. I got that on my socks. Said I was a nerd. I'm here to show up. So, physics, the study of everything around us. Physicists seem to have an equation, a diagram, for everything from the smallest of subatomic particles to the furthest reaches of space. You might think we've got it all figured out. We do not. So it turns out that matter, the stuff that we see and interact with every day, makes up only 5% of our universe. This stuff called ordinary matter. And what I work on is dark matter, which in physics is the only problem bigger than the patriarchy. Thank you. So, you might be asking, if we can only see and interact with 5% of our universe, how do we know that there is another 95%? Well, it all started in the 50s and 60s, where astronomers were having either too much fun or not enough fun. We've not quite worked that out yet, but they decided to weigh and measure some galaxies. So this is a galaxy, banana for scale. Hopefully it won't come as a surprise to you that you can't just stick these things on your kitchen scales. They are vastly enormous, much bigger than a banana. And so the way that we can measure astronomical objects is by counting up how much light there is, how many stars there are. I told you, either too much fun or not enough fun. So we know based on how many stars there are, how much light there is, how much matter there is. And we know how much matter there is, we know how much gravity there is. And gravity is pretty important. You've probably experienced it. I'd say most of you have got that sorted. So what we think is when we look at these galaxies is that the really dense, bright part in the middle has the most mass. And as we get to the edges of the galaxies, it's less bright, we've got fewer stars, things are a bit more dispersed, we've got less light, less mass, less gravity. And so they totaled all of this up, and this is really important because we also want to know how fast all of these bits of the galaxy are moving. So, say you've got a ball on a string and you swing it around in a circle. If you don't hold onto that ball very fast, it won't be very long before the ball flies out of your hand. But if you hold onto it tightly, you apply effectively more gravity on this string, you can swing the ball around really, really fast. And that's important because galaxies are big, gravitationally bound bits of space. And so we know that they haven't flown off. So we want to know how fast they're moving. And so like any good scientists, they made a graph. But unfortunately, the bit of the graph that we expect based on how much light, how much mass we can see, down here, the bit that we wanted based on an equation, and the thing that we actually observed up here, which is how fast bits of the galaxy are actually going, vary by quite a lot. And the region between these two zones is what we like to call the oh-no zone. So it turned out that there is actually a factor of 20 more mass in these galaxies than we could observe through stars alone. And even for astronomers who only work in orders of magnitude, this is too big to ignore. It's actually a secret on astronomers. So physicists wanted to work out a way to label this, right? And so one of the most popular theories is that our universe everything we can see is made of mass. So why not the things that we can't see? So we've got matter that makes up everything we can see. Everything we can't see, dark matter. Right? Physicists are super good at naming stuff. And so basically, to get this dark matter, you take the maths of how all of these particles interact and you flip it. You get a mirror image. We call this supersymmetry. You make maths take a long, hard look at itself in the mirror. It doesn't tell you anything. So physicists were like, yeah, we'll name some more stuff. Let's call it a WIMP. So this is a weakly interacting massive particle, or for those of us that speak English, it's a thing with mass. So what we want to do is collide these two pinatas and take a photo of everything that comes out of them before the kids scramble into the aftermath and take all of the lollies away. So essentially we're taking photos to try and work out which pinata these lollies came from, and from these photos work out how much mass or how many lollies we have at the end. And so if you're me, might look a little something like this. So we've got a collision, we've got some stuff that comes out, and we've got some stuff that we think is dark matter. But if you're fun and you've been to a party and you like lollies, it looks a little bit more like this. We start with our pinatas full of lollies, we collide them, we get some lollies at the end that our kids have picked up, and then we get some that just never seem to turn up until you move house in about 8 years and you find them under the couch. But it turns out that this missing energy, these missing lollies, are actually really important for us because it tells us there was something in our pinata beforehand that we can't measure, and that might be our dark matter. We might have been able to find our WIMPs. But it turns out we can't actually take a photo of them because they're vampires. This is a photo of me doing my PhD. And it turns out that we didn't find something to the extent that the title of my thesis is literally looking for something that isn't there with something that isn't there. It's not being approved by my supervisor. We didn't see anything. That is my actual conclusion, by the way. Also not approved by my supervisor. So Emily, you might be asking, why are you doing this? And don't worry, I've asked myself the same question a lot of times. But it turns out that not all physics started out as something we thought would have a practical application. And yeah, sure, discovering what 95% of the universe is actually made of is probably gonna be good, right? We've got so much stuff already. What happens if we could multiply that by 20? We'd have so much more stuff. New energy, maybe new ways of travel. Who knows? But there are also a number of other scientific concepts that didn't really come into common usage until years after they were discovered. Things like X-rays, which is why we can't use the basement of our building. Thank you, Braggs. Radio waves, which people genuinely thought were a waste of time, and now that's what all of modern communication is based on. Electricity, which I would argue, pretty important. And also the internet, which is how we lured all of you here tonight. So, the next time you're staring up into space, please spare a thought for the 95% of the things you can't see. And if we ever do find them, I will definitely be throwing a party, and it might even be the first one I ever go to.
Emily, right? Film